I'm going to be talking about techniques for finding approximations for NP-complete problems. And in particular, I am going to be showing you techniques based around something called Primal Dual Algorithms. And the reason I want to talk about this, so hopefully I can get you to be as excited about this as I am, is that seeing the primal dual property was one of those experiences that we all have sometimes in math and computer science, where we see something and it seems really counterintuitive, it just comes out of left field, and then we see a proof for it and it just makes so much sense. So for me, primal dual algorithms are kind of like that, and I wanted to share that with everybody. So what to expect in this talk, like I said, minimal salesman, a counterintuitive looking result, and then a hopefully illuminating proof. So with these caveats away and up front, let's start with what an approximation algorithm is. An approximation algorithm is something that approximates something. Okay. Let's be more specific. It is an algorithm that gives us a solution that is within some range of like the optimal solution. So to bring this back to NP-complete problems, if it was, for instance, say traveling salesman, where you're trying to find a minimal route through a graph, an approximation algorithm might give you a route that is guaranteed to be no more than twice that best possible one. And the not mentioned second half to this definition is that this approximation algorithm uses less resources in some way, virtually always time. So traveling salesman's an NP-complete problem, no polynomial time solution, but maybe you can find a polynomial time approximation algorithm. So quick aside at this point, I was using the term NP-complete. I don't know, does everybody know what that means? I'm seeing some nods and some head shaking, which is good because I got ready to say what it was. So NP-complete problems are, for the purpose of this talk, we're going to say that they are problems that we cannot find polynomial time solutions for. And that is a terrible definition of an NP-complete problem, as everyone here who knows what it means. But the important characteristic that we need here is that it's a problem we just can't solve quickly. Which leads me to another term I just used without saying what it was, and that was polynomial time. What does polynomial time mean? Well, if I wanted to be really flippant at this point, I'd say something like a polynomial time algorithm is an algorithm that's tractable, but I won't, because one, I like to think of myself as not a jerk, and also my supervisor from grad school hated it when people did that, when they would refer to polynomial time algorithms as tractable, so I'll be less hand-wavy at this point. We can think of a polynomial time algorithm, again, as just an algorithm that's going to take a roughly polynomial number of steps, where that polynomial is defined by the length of the input. So if we have, say, a linear algorithm, and we have two inputs, one's twice as big as the other, we expect the one that's twice as big as the other to take roughly twice as long to run. But if our algorithm is quadratic, and we have two inputs, one twice as big as the other, we're expecting it to take about 4 times as long. And if we made those not just not just 1 and 2, but say 1 and 10, that goes from being 10 times bigger to 100 times bigger in the case of quadratic. So polynomial time algorithms are not necessarily fast, but we can say that anything that takes more than polynomial time is definitely a slow algorithm, which is why we even bother to try to approximate them, and why we don't just go for real solutions. Okay, so lots of preamble there. Let's go to an actual problem. So here's an NP-complete problem. Vertex cover. We start with a graph. Looks something like this. And what vertex cover is it's just a set of vertices on a graph such that every edge on the graph has at least one of its endpoints in that set. So if we have this graph, and we label them, if I had, say, a set just consisting of A, B, and D, that would be not a vertex cover of this graph, because the edge C and E would have been left out. But if I added E to the set, and I made it A, B, D, and E, well then I would have the characteristic that every single edge in the graph had at least one endpoint covered. Make sense? Seeing some nods, that's good. So if we have this problem and we want to try to approximate it, well, one thing we could try to do if we wanted to, and we do because that's what we're doing in this talk, is we could take this problem and we could try to encode it as something called an integer program. All right, what does that even look like? Well, we'll start with one vertex here, x, a, we'll have this variable x, a, okay? And we'll say that xa is going to be equal to 1 if we decide to include a in our cover, and that it's going to be equal to 0 otherwise. All right? Maybe our vertices have weights. Maybe they don't. But I'll put some weights on them. Weight a, great. All right, I'll do it again for everybody else in the graph. This expression trying to find the minimum of that. Okay, so that's the goal we're trying to work to. And we want this vertex cover, we want as few vertices in it as possible, or if they have weights, we want the lowest weight one, great. But how do we encode the fact that we need every edge to be covered? All right, well, we'll take a particular edge, A and B, for instance, entirely arbitrary. And we're going to say, well, I need xa plus xb, and I need that to be greater than or equal to 1. All right, so this, if I get this constraint to be satisfied in whatever solution, whatever assignment to my x's that I come up with, if I get this to be true, then I know this edge is going to be covered. If, for instance, both a and b, both of those vertices aren't in our cover at all, then, well, xa is going to be 0. And xb is going to be also 0. 0 plus 0, well that's 0, and that's not greater than or equal to 1. So this tells us that, all right, if my assignment satisfies that, then this edge is going to be covered. And I'm going to do it again for all the other edges. So I need xa plus xc greater than or equal to 1. And I need xb plus xc greater than or equal to 1. C, 6. I've made it so far without being curious. D greater than or equal to 1. Great. I made a picture and some words that I just said out loud into this nice mathy looking expression, and I got this integer program, and integer programs are in the arbitrary case NP hard to solve. So what was the point? What did we just do? Well, we could maybe relax some of these constraints. Maybe we could take something and make it a little easier on ourselves. So in particular, if we get rid of this constraint, if instead we just say, I need xi to be greater than or equal to 0, then, well, then this is not an integer program anymore. This is a linear program. And linear programs we can solve in polynomial time. Now, it's beyond the scope of the talk for me to explain how you solve one of these in polynomial time, so let's just assume that we've gotten a solution back out. And we have some set of xi's, they're all greater than or equal to 0, and we know that they satisfy all these constraints, and this is the minimal value that we can possibly find that satisfies these constraints. Well, now we're going to take that solution, and we're going to try to build a solution to the integer problem. And it so happens that Vertex cover has the really nice property that all we need to do to translate is to round up. So if xi is greater than or equal to 0.5, round up. And if xi is strictly less than 1/2, round down. Okay, that seems like a thing we could do. Does it work? Well, yes, otherwise I wouldn't be here, but let's think it through. Let's go back to that first edge, xa and xb. So are we guaranteed that at least one of them is going to be greater than 0.5? Because I said I'm going to round one of them up. I need to round one up in order to satisfy that constraint. Well, if they were both less than 0.5, if I have two things and they're both less than 1/2, and I'm adding them together, I'm going to get something that's less than 1. And if I have something less than 1, that thing cannot be greater than or equal to 1. Okay? So I'm guaranteed that at least one of xa and xb is going to be greater than or equal to 1/2. Otherwise, the whole thing wouldn't work. All right? So when I round up, I'm going to get each of these constraints is going to be satisfied. Okay? So if all these constraints are satisfied, and all my xi's are 0 or 1, then I've got a solution. I've got a solution to the problem. And it's going to be a real solution, not with these fractional values. Okay, but how bad is that solution? Because it's not going to be the optimal solution. Otherwise, we all kind of go home at this point. But how bad? How bad can the solution be? Well, the first thing we're going to say is that if we solved this using these linear variables, where xi could be any value, this expression here, this minimized expression, well, this has got to be a lower bound on the optimal solution when we have integers. That makes sense? I mean, if the solution came out to, say, 2.5, which it actually would for this, assuming equal weights, I know that I can't possibly find a solution with just 2 vertices. Because if I could find a solution to 2 vertices, then when we were figuring what the minimal value would be with arbitrary xi values, it would have had to consider the solution where the xi's were integers and there were just 2 of them equal to 1. So, in the particular case where it comes back 2.5, I know that my optimal solution has to be at least 3. Maybe it's not 3, might be more, but that's what I know. Okay. So what I'm saying is that this value here is going to be a lower bound on the solution for the integer program. Okay. Well, how much might we have increased this by? Well, sometimes we round stuff down, but we do not live in a merciful universe. We can't assume we rounded anything down. Sometimes we round things up. And the worst case scenario is that I have xi equal to 0.5. When xi is equal to 0.5, we're going to round up xi to be equal to 1. So we're going to double that value. So that means in the worst case scenario, where every single xi came back as 0.5, we rounded every single one up, we're going to get this expression coming out to twice as much as it was before. Okay, so if I have something that is a lower bound on my optimal value, and I've just got something that I know is going to be twice as much as that, in the worst case, then I can say that it's going to be bounded above by twice the optimal. Okay, so just simple rounding like this, and we've talked ourselves into an approximation algorithm that's at worst twice as bad. All right? And there's sort of a whole class of approximation algorithms that you can do with these rounding tricks. You can use different strategies for rounding, randomized rounding. You can be a little bit more clever about how you set this problem up. But that's not what I really want to talk about. What I really want to talk about is this other technique where we're going to do something even crazier. So, again, we've got the same problem here as a linear problem. And we're going to propose this second problem. And the way it's going to work is, so each of these constraints kind of corresponds to one of the edges. So if I were to label my edges, 6, you know, this constraint here, well that's like edge 1, and this one here, that's like edge 2. And just for the sake of sort of bookkeeping, even though all of these are 1, I'm going to pretend they have actual values. So V1, V2, V3, 4, 5, V6. Okay. We're going to have this other problem. It's going to look really crazy. Come with me on this journey. I'm going to say for each edge, I'm going to have a new variable in this whole second seemingly unrelated problem. And that's going to be y. Say y of 1. And I'm going to have a whole bunch of these. So I'm going to have, you know, 1 for each edge. 2, 3. More space in front of that y. I also never realized how bad I was at doing uppercase y's. So I have these new variables, and they're going to correspond to each edge. And then I'm going to take the weights from these variables from the corresponding constraints here. Okay? Really badly positioned these plus signs. Thought I'd be all smart and leave spaces for myself. Okay, and then I'm going to take, lump them in at the max of this expression. Okay, what about constraints? Also, yi greater than or equal to 0. All right. What about constraints? Well, I'm going to build constraints that look kind of like these. I'm going to build a constraint for every single one of my vertices. Yeah, that should work. I mean, I built constraints for each edge here. I can build a constraint for every vertice down here. All right, what's the weight going to be? Well, I'll take the weight off the vertice. All right, so weight A. And well, these were greater than or equal to's. So let's make these less than or equal to. What should I have over on the other side? Well, in this one, I included every vertice that was adjacent to an edge. So why don't I include every edge that's adjacent to that vertice? So for A, I got edges 1 and 2. So I'll say this has to be less than y1 plus y2. All right, and then I'm going to repeat that a whole bunch. So that was A. B has 1 and 3. And that'll be less than or equal to the weight of vertice B. And C is kind of long because there's lots of edges that touch it. All right, and I'm going to propose a crazy way of picking which vertices I want to pick. So I'm going to pick an edge that hasn't been satisfied, say edge 1 entirely, arbitrarily, and then I'm going to increase the variable down here that corresponds to y. I'm going to increase it until one of these bounds becomes tight. And then I'm going to repeat this. Oh yes, what's going to happen when that bound becomes tight? So a bound will become tight down here as I increase y. Maybe two will become tight at once. Don't worry too much about that possibility. We increase, a bound becomes tight, and then we decide that we're going to include the vertice that corresponds to the bound that becomes tight. So say we increase y1, and y1 was here and here. So say WA was less than WB for some reason. We increase y1, increases. We hit the point where it's equal to the weight of A, and we say, okay, I'm going to include A in my cover. Because that bound became tight, XA is going to be equal to 1. All right? Well, XA is now equal to 1, but this is still not like a valid vertex cover. We're still not covering everything. So we'll find some other edge that's not covered. So say we picked 5 the next time. And then I'm going to increase y5 until some variable becomes tight. Well, maybe we'll make it a little more interesting. Say I said y2 or y3. Well then, it's not just a question of like increasing y2 until it's y3, say, until it's equal to WB, because we already have the value of y1, so we might not have to increase y3 by very much. But when that happens, and that bound becomes tight, then we decide, okay, I'm going to include xb is going to be equal to 1 now too. And I'm just going to repeat this process until we have no more uncovered edges. All right, so if I do that, do I have a valid vertex cover? Well, I kind of just said I did. I said that I went until I had no more edges that were uncovered. So that's a valid cover. Okay, well, how bad is the cover? I mean, that thing I just described doing, that's pretty polynomial time. Pick an edge, increase a value, based on that, make one of the vertices 1. Okay, well, how bad is it going to be? Well, this is the expression we care about here, this minimization. So we're going to have, yeah?
When you're increasing values and you hit some limit, how do you decide which vertex to include?
Oh, so these weights here, so like say this one right here, for example, this is the variable that corresponds to this edge, and this is the variable that corresponds to this edge, and this weight and this whole constraint corresponds to this vertex. So like each of these constraints corresponds to a vertex. When that's the constraint that becomes tight, that's the vertex we include. Make sense? Wonderful. Okay, we're going to do some real math now. All right, so I've got this like sum of the weights and x's. That's the thing that I have. I picked out a bunch of x values, so here we are. And I want to figure out how much it is. Okay, well I'm going to get rid of the x's that aren't equal to 1. So I, such that xi is not equal to 0. So I excluded all of the x variables that I didn't decide to include in my cover. I can get away with doing that. I mean, if xi is equal to 0 over here, it's not adding anything to the sum, it's just 0. So we can do that. Okay. Well, what can I do next? Well, now I can do something that looks a little crazy. Actually, I don't think I really have enough space. I may have to erase this part. Or at the very least, I'm going to have to erase the edges of these problems. Imagine there's some dots here. So I had my xi's, I had their weights, and I had excluded the ones that are equal to 0. And now we're going to do a weird looking thing. Okay? I still got this part of the sum, that's going to be the same. But I'm going to replace wi with this sum j such that ij is an edge of ij. Yes. All right, what's this crazy looking thing that I just did? Well, what this expression is it's the sum of y's such that j is one of the endpoints. Or rather, sorry, such that I is one of the endpoints, and we're summing over all of them. Why can I do that? Well, remember why we decided to include xi. We decided to include xi because one of those constraints became tight. And what's on the other side of this constraint? Here's this wi, here's the corresponding w. What's over here? Well, what's over here are all the edges that were adjacent to that vertex. So I know that this expression has got to be equal to wi, because that's how I decided to include xi. Okay, so I can get away with that. Seems fair. All right, I'm just going to bring xi into the sum. All right, such that xi is 0. Such that ij is an element of the edges. Ij is I. Alright, just brought xi inside the sum. That's something I could do. And now I'm going to rephrase what this sum here is a little bit. It's a little clearer what's going on. Such that xi is 0. Sum over edges such that I is in that edge of ye xi. So just in turn, I just changed it from saying, instead of expressing the edge as a pair of vertices, we're just saying, here's this edge, and these are all the edges that have I adjacent to them. Just the same thing as up there, just rewriting it. Okay. And now I'm going to rearrange the, now I'm going to start including zero-valued xi's again. So this is now the sum over all vertices, the sum over all edges, such that I is an element of that edge, y edge xi. And I can put back in the zero-valued xi's for the exact same reason that I could take them out in the first place. They're equal to 0, so that's fine. All right, now I'm going to rearrange the order of this summation. So we're summing over our edges. And now instead of it being, we're now going to say, okay, this is also going to now be the sum over I, such that I is an element of that edge. And we've got the same thing on the inside. We've got y, e, xi. Now I'm going to pull the same trick. I'm going to pull y, e out of the expression. No, I do not have enough space here. Sum of all edges. I'm going to do a thing that might seem a little counterintuitive. I'm going to say that this is less than or equal to the sum for all the edges 2 times ye. All right, why am I allowed to do that? Why am I allowed to suddenly replace these sum of xi's with 2? Well, remember what these xi's represent. This sum of xi's, this is the sum of all the xi's such that I is in some edge. So say we're looking at maybe edge 1 here. Well, edges are only ever going to have two vertices adjacent to them. That's how edges work. So at most I'm going to have two of these xi's in here. And we know that their values are either 0 or 1, and at least one of them is 1. So this sum is either 1, because all the edges are satisfied, or maybe it's 2, if we happen to have included both of the vertices. Okay, so if this expression is at most 2, then I can do this. I can just replace it with 2. All right, so I've done some math. Hopefully we've all followed it and it's been okay. And now we're going to make the crazy jump. Because we're going to say, well, okay, sum of over 2e, well, that's just equal to 2 times the sum of all of our y'e's. And yeah, that's less than or equal to 2 times opt. Right. That's the crazy step. That's the step where we're like, what? Yes. Was that a hand or? Okay. Yeah, we're going to explain why that just happened. Okay. So we did that. Why do we get to do that? Well, we're going to take a step back and we're going to go with a much more general version of this problem to show why we can get away with doing that. But I'm probably going to have to erase a lot of this, but I want us to remember what our conclusion was. So the important bits, after we skipped over all of this, is that we said that some of the weights I less than or equal to 2 times the sum of y'e's, and that was going to be less than or equal to 2 times opt. So keep in mind that that was the conclusion that we had. I'm going to write something that looks like a more general version of that problem that we used to describe vertex cover. So, still a minimization problem, okay? And we've got some x's again, great, and they've got weights. I'm going to call those weights C this time. Constraints just like before, but this time those constraints are going to be even more general. We're going to have some variable a, 1, 1, x1 plus a, 1, 2, x2, a, 1, n, xn. That has to be greater than or equal to some value b1. And then we're going to do it again. a2, 1, x1, a2, 2, x2, a2n, xn, greater than or equal to some b2, a1, x1, a2, x2, okay. Xi is going to be greater than or equal to 0. And from this, okay, I'm going to build a primal problem that's going to, like this is our primal problem, and I'm going to build this dual problem that is going to be based on all of this again. And it's going to look very similar to the dual problem that we made up with our vertex cover problem. So we're going to have a maximization, great. And we're going to have these variables y, and they're going to come from these m expressions here. And their weights are going to come from here too. So b1, y1, 2, y2, bm, ym. And we're going to have these constraints again. They're going to look just the same. So this time, this wasn't as obvious in the vertex cover problem, because in the vertex cover problem, all of these a values were 1. but we're going to bring them down here too. So again, we have A1, 1, Y1. So this time it's going to be A2, 1 instead of 1, 2. And if you're thinking transpose, you're thinking correctly. You know, if you happen to have paid more attention in linear algebra class than I did, and that's obvious to you at this point, it wasn't obvious to me at this point. Less than or equal to C1. All right. So I could be exhausted, I could write out these, but are we good with me moving on to the next part? Okay, I see some thumbs up, which is good. This is tedious to write down. Okay, so what I'm saying in another format here is, well, C is equal to this thing here, and B is equal to this thing here, and we've got X equal to this, and Y equal to this, and we have this matrix here, A. We're saying that we have A of X is greater than or equal to B, and A transpose of Y is less than or equal to C, and we're trying to minimize X times C, and we're trying to maximize Y times B. And we have this cool thing called the weak primal dual property that lets us say that this is greater than or equal to that. And again, we're in this like, well, why on earth would this apply? I mean, these are entirely arbitrary expressions. They're not, I mean, they're related, obviously very related to each other, but somehow or another we get this property out, which is like the magic part. So, okay, where do we go from here? Well, we're about to just do a bunch of rather tedious looking algebra once we get started. Okay, so again, we just start off with this like sum over I of Ci xi's, so just that over there, okay? And I'm going to say that that's greater than or equal to Why am I allowed to do that? Well, we said that these expressions over here were less than or equal to their corresponding values of C, so I can just replace Ci with this row here, and that's just this expression. That's what those rows correspond to. Okay. All right, I got the y's and x's in there now, so that's something. Okay, and then I'm going to bring the xi into the expression again. All right, and then I'm going to reorder I and j. I can get away with that. But notably, we're going to keep the order on this A, J, I thing the same. A, J, I, Y, J, X, I. All of this seems like things I should be allowed to do. Now we're going to move Y, J out again. Okay, so this is the sum over j, sum over I, AJI, XI, YJ. And then I can say that that is going to be greater than or equal to sum over j, DJYJ. All right, why am I allowed to do that? Well, this sum here, these A's and X's, that's just this row up here. So since I said that this expression was going to be bounded below by that VI, I can just put it over here. So there we go. We've basically said that if we have some arbitrary expression of x's and some arbitrary expressions of y's that satisfy these pairs of constraints, we have that this minimum here has to be greater than or equal to this maximum over here. All right, well, how does that bring us back to having 2 times the optimal? Well, we said, to make this a little bigger again, that we had xi less than or equal to 2 times the sum of the y's. Well, these y's, they're not even necessarily going to be the maximum. They're just some arbitrary one. So they have to be less than or equal to the minimum possible value that these xi's could, these sum of x's could take on. So since this part there has to be less than even the smallest possible value of this when our xi's are allowed to be any arbitrary value that we want, that's how we can conclude that this has to be less than or equal to 2 times opt. That's how we get there. So, as with rounding, there's more you can do with this. There's sort of more intelligent ways that you can build a solution to your primal problem from your dual problem. There are better techniques for generating what the problems look like. But they all come down to this fact where if you build a problem that looks like this and you build another problem that looks like this, the smallest possible solution to this one is going to be bigger than the biggest possible solution to this one. And that's how you use the weak primal dual property to build an approximation algorithm for an NP-complete problem.
Yes? Where was this research published? Or is there a particular paper I should go look up for this?
So I actually learned about this from a Coursera course,
Okay.
of all places. There is one offered by ENS, which is a research institute in France, and they just have this pair of really great courses on approximation algorithms, and that's where I learned about this from. Trying to think roughly, they talk a little bit about when the papers are, but I do not remember what paper this particular thing came out of. Yes?
You mentioned in private that Vertex cover is not actually a great example of this because the dual bound is not really any better.
It's not any better than rounding.
Is there an example of a problem where it does?
Steiner-Forst. That was the problem in the course that they first used to kind of demonstrate this. I'm trying to remember the exact values, but basically, if you try to use a rounding-like approach, you kind of get nowhere. You just don't get a good solution at all. You can't build a constant time approximation at all. But if you use this technique, you are able to build something.
It's a 2 approximation. It's a 2 approximation.
It's also a 2 approximation. Thank you. Yeah.
So there's this equivalence between NP-complete problems as far as their runtimes go. Is there also an equivalence between them as how primal dual approaches work?
Not so well. I'm not sure about primal dual specifically. I know in general for approximation algorithms, the answer is no. There's some NP-complete problems where, for instance, we're able to construct ways of getting arbitrarily good approximations, and there's other NP-complete problems where we don't have that characteristics as much. So I'm not actually sure. I don't know the answer to that one, whether or not it's true with Primal Dual Algorithms in particular. And part of it is we get a little bit lucky in Vertex cover, because we were able to basically say, well, the value of x is going to be bounded, when we're weird and arbitrary, is going to be bounded above by 2 times this like sum of y's for any y at all, no matter what. Whereas we don't necessarily have that. It depends on the problem. There were parts of this that we were able to assume, in particular the bit where we got the 2, and we were able to get rid of our x's, that was a characteristic just of Vertex cover. And there may or may not be something equivalent for any given NP-complete problem.
The trick with NP-complete problems is that we always think of them as being equivalent with respect to their runtimes, because said runtimes are so big that it's like, oh, you look. But the actual equivalence relations for most NP-complete problems, most other NP-complete problems, have additional runtime factors that, when you reduce it to a polynomial or lower approximation,
Start to matter a lot.
overriding.
Yeah.
Because otherwise you could just say, well, they're all equivalent, so I can convert any NP-complete problem to the vertex cover problem. That is demonstrably possible. So I'll just do that and then use this. Except that the conversion process takes longer than you want a double algorithm.
Unless you take a polynomial hit there.
You take a very big
Your
polynomial
Your
hit.
function gets polynomially times larger.
Yes, exactly.
Yeah. Like this is like not, this is fairly quick to do. I mean, I think you're around quadratic, but I mean, if your conversion is like a quartic of x to the 4, suddenly you're at x to the 6, and you should go home. Any other questions?
So how you do about practical algorithms? Yeah, can you use some of these techniques to, if you have an approximation algorithm, that means you can tackle an NP-complete problem and find a practical algorithm. Yeah.
Yeah. Well, that's a major reason why approximations for NP-complete problems is such a popular thing, is that we're pretty sure we're never going to get a polynomial time solution to any of this. So if we're faced with an actual problem, well, we start asking ourselves, how good does our problem actually have to be? In the case of vertex cover, twice seems kind of terrible with the example I just showed you, because we had 5 vertices. The actual one I showed you, if you had equal weights and you solved that one, they all come out to 0.5. So the solution would say, choose all the vertices. But, if you had instead something like a star pattern, where you had like one vertex in the middle and a whole bunch of vertexes all pointing at that one, either the rounding or like this more elaborate thing is going to give you the optimal solution of just take the one in the middle, please.